Good morning. Let us see today reaction quotient. What is reaction quotient in chemical equilibrium and thermodynamic treatment of chemical equilibrium? What is the effect of temperature on chemical equilibrium that is given by band of equation and the activation energies for forward and backward reactions. Let us first see reaction quotient. It is represented by letter Q. Let us consider a reversible chemical reaction. AA plus BB gives CC plus DD. Then the reaction quotient Q equal to the ratio of products divided by and the reactants Q equal to, that is at any other stage away from the equilibrium. Q is the equilibrium at any stage away from the equilibrium. Okay. Suppose when K, there are three cases. First case, Q equal to K. When Q is equal to K, the equilibrium is at equilibrium. That is, the reaction is at equilibrium. Q equal to K. At equilibrium, Q equal to K. Equilibrium constant. The second case is Q is greater than K. When Q is greater than K, that means when Q is greater than K, the products are more than reactants. The products are more. The numerator value is greater. Okay. Therefore, the reaction proceeds in the backward direction so as to decrease the concentration of the product to reach the equilibrium. So, at this condition, Q tends to decrease, therefore favoring the backward reaction. Similarly, opposite, Q less than K. If Q is less than K, then the products are more. The products are in larger concentration than the reactants are larger concentration. Q is less, therefore the reactants are in larger concentration. Therefore, the equilibrium shift in right direction, in forward direction, so that the reactants are consumed, reactants are decreased to reach the equilibrium value. Okay. According to Quotient principle, it will tend to, the equilibrium will adjust in such a direction so as to decrease the increase in concentration or decrease in concentration. Okay. Let us see thermodynamics of chemical equilibrium. We have already seen this delta G, new chemical potential in terms of chemical potential. Delta G equal to delta G naught plus 2.303 RT log Q. At equilibrium, Q, the reaction quotient, is equal to equilibrium constant. Therefore, delta G equal to 0. At equilibrium, delta G equal to 0. Therefore, we know that delta G naught equal to minus 2.303 RT log K. This equation we have already shown, band of reaction isotherm. We also know that delta H naught equal to delta G naught equal to delta H naught minus T delta S naught. We can substitute. Several problems were asked based on this. Let us see the effect of temperature on the chemical equilibrium. Van Gogh has derived a mathematical equation to study the effect of temperature on the chemical equilibrium. In thermodynamics, we have studied d ln k divided by dt equal to delta H naught by RT square. This equation is called Van Gogh equation. This gives the effect of temperature on the chemical equilibrium, where delta H naught is the heat of reaction at standard condition, where R is the molar gas constant and T is the temperature. Now, let us take Tt here, Tt by T square. On integrating this, for example, at one temperature, then ln k equal to minus delta H naught by RT plus integration constant. RT, that is dx by x square, equal to minus 1 by x plus c. Therefore, c is integration constant. This is a straight line equation. Therefore, on plotting ln k y, this is and this is 1 by t is x. a straight line with the negative slope is obtained with the intercept constant c and the slope is equal to minus delta H naught r. Okay. Now let us integrate between two different temperatures. At two different temperatures, at temperature T1 the rate constant is measured and you rise the temperature to T2, the rate constant is measured as K2. Then on integrating this, okay, you will get log K2 by K1 and delta H naught 2.303, okay, so here 2.303 and 1 by T2 minus 1 by T1 will come, but minus sign is there, therefore 1 by T1 minus 1 by T2, but T2 is greater than, the temperature T2 is greater than T1. Okay. Now there are three cases when the heat of reaction equal to 0, when on substituting in here delta H not equal to 0, this will become 0, therefore log K2 equal to log K1, that is K1 equal to K2. At two different temperature K value is same, therefore there is no effect of temperature on the chemical equilibrium when delta H naught equal to 0. When delta H naught is greater than 0, that is delta H naught is positive, this is an endothermic process. This is an delta H naught is greater than 0, that is K2 endothermic process. Therefore, on substituting here, you will get log K2 greater than log K1, that is K2 greater than K1. Therefore, at the temperature is greater, the K value is greater. The temperature is greater, the K value is, the equilibrium constant is greater. In the third case, for delta H less than 0, that is endothermic, this is just opposite, K2 less than K1. Okay. Next, activation energies for chemical equilibrium reactions. There are two opposing reactions. There are two reactions, forward reaction and reverse reaction. Therefore, there are two activation energies. There are two activation energies involved in it. Activation energy for, this is the energy profile diagram for exothermic reaction. For example, forward reaction is exothermic. Let us consider. Then this is the energy of the reactant. This is the energy of the product. In y-axis, reaction progress is taken. This is x-axis and this is y-axis, and delta E equal to EP minus ER, therefore delta E equal to negative. Delta E equal to negative, this is an exothermic reaction. This is the activation energy for forward reaction and this is the activation energy for reverse reaction. Therefore, at constant volume delta H equal to delta E plus P delta V. P delta V is equal to 0, therefore delta H equal to delta E for exothermic process. EAF is greater than EAF is less than, EAB is greater than for exothermic process. For endothermic process, it will be opposite, that is the activation energy for forward reaction is greater than the reverse reaction. We have already studied the Arrhenius equation in chemical kinetics. Please watch the lesson. So these are very important for solving many of the competitive exam problems and also semester exam problems. Thank you for watching.